So simple band brake is designed to stop the rotation of shaft, which is transmitting at a power of 50 kilowatt at an RPM of 600 RPM. Okay, the diameter of the drum. Okay, the band brake, the diameter is drum is 600 mm. The angle of contact of this band on drum is 225 degree. And total length of the lever is also given as 1000 mm. So then the distance between the fulcrum and other end of the band is 300 mm. So how does it look like? I will show you the figure. And other details that's given is the drum rotates in the clockwise direction, and the free end of the lever is at the left side of the drum. That means the point of force, that part is called the free end of the lever. That's on the left side of the drum. So you have to select the suitable material and determine the band dimension, brake lever dimension, and the diameter of fulcrum pin. So how to solve this problem? So these are all the given condition. We have power 50 kilowatt, RPM 600, and diameter of the drum is also given. And theta, the angle of contact, that had to be converted into radian. We cannot solve by using degree. We have to convert into radian in order to solve the problem. Then this is the figure according to the condition. We can see they mention the distance between the fulcrum and the other end of the band. This is the other end of the band. So that distance is 300 mm. Total length of the lever is 1000 mm. Okay, so this much 300, total is 1000. And also mention there's a clockwise rotation. These are all the given condition. So and the first thing we have to find is the band dimension. So band dimension means basically you have to find the width. Okay, width of the band is what they actually mean band dimension. So that can be found by this equation. This equation is also in the data book. So you need to find the individual term in it. So sigma d, the design stress or the material stress is not given. They already mentioned we have to select a suitable material. So based on that, I'm assuming the design stress is 60 megapascal. Okay, then the value of H, that can be found by this equation 0.05 into D. You know the value of D, drum diameter. So you get the value of H as 3 mm. So then what you have to find is we need to find torque. Okay, torque is basically force into distance. So here the drum is basically the torque in the drum is due to the difference in force on the tight and slack side. One end have fulcrum, other end it's tight, so there will be a tension difference or force difference at the two side of the drum. This tension difference is what actually causing the torque in the drum, okay, or band. So that torque can be found by Ft into R. Ft is either tangential or the difference of the force F1 and F2. So here we can take it as T is equal to Ft into R. So how do you find T? T can be found by the equation 2 pi nt by 16. We know that the power equation. From that T can be find out when substituting will be we will be substituting it by I mean converting. Either you can directly get the answer in Newton mm, or if you convert it into SI unit, you have to write it again in Newton mm. So now we got torque. So we need to find the value of Ft. Okay. So how do you find Ft? We know the value of R because the drum rate is 600 mm. So obviously R is 300. So Ft will be 2652 Newton. So why do we find Ft? We need to find the force on the tight end and the slack side. So F1 is always the high tension one, F2 the low tension part. So you can see from the figure, since it is in clockwise direction, obviously this part will be having higher tension than this one. Okay, you have to keep that in mind because this is in clockwise rotation. Okay, so this drum is moving like this, so this part will be experiencing more tension than this part. That's the general uh, convention will be taking. Suppose it is in anti-clockwise direction, this part will be having high tension. Here it is clockwise direction, so F1 will be having a very high tension. Also, this force applied on the lever is also not given, or its direction is not given. Here also assumed in the downward direction because they already mentioned clockwise direction as the direction of rotation. In order to stop the rotation on the clockwise direction, you have to apply a force downwards. That's the reason why F is acting downwards. This is the equation to find the force on high tension. This equation is also in the data book. We don't have the value mu, but we can assume just 0.25. So remaining all the terms we know the value 50. So we can find the F1, the force on the high tension side as 4246 Newton. Similarly, you can find the force on the low tension side F2. This equation is also in the data book. So now we got both F1 and F2, but in the width of the band, we only need F1. Okay, we don't need F2, so you can substitute F1 and find the width of the band as 24 mm. The next, the second part is we have to find the lever dimension. That is what they asked in the second question. So before that, you should know some terms. H1 will be the depth of the lever, B1 will be the width of the lever. So this will be the equation, basic equation between the moment, inertia, stress. This basic equation will be taking to solve the problem. So each term you need to find. So I is the moment of inertia. Here in this case it will be bhq by 12. Okay, I just written as b on h1, but generally it is bh by q 12 in the case of band. Okay, based on its thickness and width will be this equation. You don't know the value of h and the relation between h and b we don't know, but we are assuming it be h1 to be 3b1. Okay, this is general convention. If you don't know, if it's not the data is inadequate in the question, you have to assume this term h1 is equal to 3b1. Amount of inertia will be 2.25 b1 raised to 4. Next term we need to find is c. That distance will be h1 by 2. This is also not given, but this equation is known, so you have to learn this. C is equal to h1 by 2. So h1 already assumed as 3b1, so z equal to 1.5 b1. Okay, the material of the lever is not given, so I'm assuming to be C45 be the material. So based on that, the yield stress will be 353, and factor of safety is also not given. This is also assumed to be 4. So from there you can find the sigma as 353 by 4, the yield stress by factor of safety. This is the basic equation. We get stress as 88.25 megapascal. This is the next part we are doing. Not to based on the equation we need moment, right? M. So moment is force into the total distance, but how do you take the force? Here one thing you have to notice is I already mentioned the direction is clockwise direction. Suppose if there was not they have not mentioned the direction, then we need to find both the clockwise and anti-clockwise condition. Here they have mentioned it as clockwise direction. So based on that, this is a convention we know, right? So the basic convention is suppose the force and the direction of rotation are the opposite direction, will be taking the clockwise equation. If the force is in no direction, you know that, and the rotation is in clockwise direction. So these two are in the opposite direction. So we can only take the equation of clockwise equation, not to take the force as a general law when we are taking the force equation. Suppose the force and rotation are in the same direction, we'll be taking counterclockwise equation. Here they are in opposite direction based on the figure, so we'll be taking clockwise equation, and this is the clockwise equation of the force. We know ft b is the distance between the fulcrum and one end of the band. We know that total length a, we know mu, we know theta, we know all the values. You get the value of f as 478 Newton. So from there you can find the moment. Okay, moment will be force into that distance, and that also should also be Newton mm. Alright, so you got the moment. Next part is simple. All you have to do is substitute in that previous equation. You'll get the value of b1, that breadth of the lava, that will be 16 mm. Then h1, the depth, we know that relation, we have already assumed h is equal to 3b, right? So since we got b, we have to substitute and find the value of h. We got the lever dimension. Let's look at the third part of the question. This is the third part of the question. So this part you have to look a little bit serious. We are asked to find the diameter of the fulcrum pin. So not to determine the diameter of the fulcrum, we have to draw the free body diagram of the force acting on the that lever. So this is the point of the fulcrum. Say for example O. So based on this figure, you know F1 here will be F1 because it's we already know this is 300 meter apart. Okay, this is 300 meter apart. So this will be F1 because that force will be higher, and F2 the other one will be F2 that will be lower. Based on our figure, this will be the force component. So F2 will be inclined to this part. There will be an Fy and Fx component on the fulcrum, and there's already F1 and F2 here. And this F is the general F, I mean the force applied on the lever. So all I have to do is just split into component and applying the force equilibrium. This is the detailed, I mean component, I mean diagram of the hinge, I mean point O, fulcrum point O. Okay, this component you can see this F2 can be converted into two component. Adjacent will be cos 45 component. This will be the sin 45. Okay, this direction you have to remember. This will be always in like this towards the force. So Fx will be in this direction. Fy will be in downward direction. Even if this whole figure is reverse, you just have to follow this convention. Okay, this Fx component will be always towards the force applied. So considering horizontal force, there will be only this F2 sin 45 and Fx. This will be equal to each other. So from that we can find the value of Fx. Similarly, you can consider the vertical component. Okay, the upward force and downward force. So that from that you can find the value of Fy. Now we got both Fx and Fy. Now you need to find the resultant force on the fulcrum. Can be found out by the general resultant equation square root of Fx square plus Fy square. So we got the resultant force at the fulcrum. Okay, but that is not the question, right? We need to find the diameter of the fulcrum pin. So how do you find that? The one thing we have to notice is the pin is subject to double shear. Always remember that the pin is subject to lever pin is subject to double shear. So we know the equation of basic equation of shear stress, shear force by area, right? So the area we cannot simply write it area. You have to multiply it by 2 because it is having a double shear as a known fact. Okay, as a known fact, this fulcrum pin is having a double shear. With the single shear, you don't need to put the value 2, but in the case of an band break, the fulcrum pin is having a double shear. So you need to put the value. You have to multiply it by 2 on the place of area. This is simply force by area. Okay, the force, this is the resultant force, that's only difference. Okay, force by area, but the area we have to multiply it by 2 because it is having a subject to double shear. That's a known fact. We have to take that in all these type of question. All right, but we don't know the value of shear stress. We only know the value of normal stress. There's a relation between shear stress and normal stress. Is this value, this equation is also in into by heart, that shear stress will be 0.5 into sigma. Okay, you know the value of sigma. You already find that earlier. So simple, you get substitution. You will get all of the, we know all the factors. We know the area. This pi d square by 4. We know d. So substitute and you get the value of shear stress, and we find the value of dp, diameter of the fulcrum pin. Okay, that's only step we have to do. Just substitute and find the value of dp. So the diameter of the fulcrum pin will be 9 mm.